Okay, today we're going to cover the last new topic of the chapter. After that, for the rest of the week, we'll do some review stuff and get a quiz in on the second half of the chapter. The quiz will start with PV equals nRT, that ideal gas equation, and go all the way through this that we're going to cover today. But we'll do some review of that over the next couple of days. Maybe take the quiz Wednesday or Thursday, probably Thursday. So, the last gas law that we have to talk about is Graham's law. Everybody gets their name on a law these days. Graham's law deals with the diffusion or effusion of a gas. We'll look at the difference between those terms, like how a gas spreads out around a room. Example I like to use, if you're in my classroom and I'm standing in the front and I open up a canister of cyanide gas and a canister of nerve gas, because I'm a supervillain, they're going to start expanding and diffusing through the room, and eventually they're going to get to you. So which one kills you? Which one gets to you first? That's what Graham's law is all about, how fast gases diffuse. The example they use is a little less deadly. They use perfume bottles instead of poison gases, but they're not supervillains like me. Now, diffusion is the spreading out of gases through the air. Specifically gases. It could be diffusion of like a dye through water or something like that too. But for our purposes here, we're worried about diffusion of a gas through the air. That's going to be governed by, well, the motion of the molecules. If the molecules of the gas are moving around really fast, then they're going to diffuse quickly and get to you quickly. If the molecules are moving very slowly, they're going to obviously get there a lot more slowly. Now, that speed of molecules, remember from kinetic molecular theory, is the temperature. So, first of all, if I want to compare gases to each other, they better be at the same temperature. If they're at different temperatures, it's not a fair comparison. The hotter one has faster moving molecules and an unfair advantage. So for the rest of our discussion here, we're going to make sure all the gases are at the same exact temperature when we compare them. Now, if they're the same temperature, are they going the same speed? Not necessarily. Same temperature means the same kinetic energy. Well, average kinetic energy, but we'll go by the average here for molecules. So they have the same average kinetic energy. If you remember from physical science, maybe in middle school or whenever you did that, kinetic energy depends on mass and on velocity. In fact, it equals 1/2 mv squared. You don't have to know that equation. We're going to derive our own equation later. But the important thing is it depends on the kinetic energy, depends on the mass and the velocity. So at a certain kinetic energy, meaning whatever temperature we're at, if you have molecules with very low mass, they're going to move faster. And if you have larger mass, they're going to move slower. If you think about it, if I want to throw a very massive bowling ball at you, again because I'm mean, it's a massive object. Whatever energy I can impart with my super strong muscles will determine how fast it's going to come flying at you. If I want to throw something lighter at you, maybe only a baseball or a golf ball, well, I'm using the same amount of energy in my muscles. They didn't get any stronger or weaker. But I'm going to be able to throw the baseball at you a lot faster because it has less mass. So with the same energy, which is the case when you have equal temperatures, the more massive particle is going to be moving slower. And that applies to molecules too. Okay, now, they want to get the definitions out there formally. Diffusion is the movement of gas molecules, and they go from areas of high concentration to areas of low concentration. If you have your perfume bottle open, the area right around the bottle is highly concentrated with perfume vapor. The air on the far side of the room has very, very little perfume vapor in it. So over time, the perfume molecules will diffuse or move from that area of high concentration toward the areas of lower concentration. And eventually they'll uniformly fill up the whole room. And the whole room will stink of whatever perfume you're using. Here they give an example where they show bromine gas down here. Bromine has that brownish orange color to it. And then there's just air up top. And if you give it time, the bromine vapor gradually diffuses up and mixes thoroughly with the air. That's what diffusion is all about. Now notice bromine molecules, whatever temperature we're at here, move at a certain speed based on their mass. And so it took whatever number of minutes for it to go from here to finally thoroughly mixed. What if I was using a heavier gas, like maybe iodine vapor? Well, those heavier molecules, iodine has a bigger molar mass than bromine. Those heavier molecules are going to move more slowly. So it's going to take them longer to get from here to partially mixed. And it's going to take them longer still to get to here thoroughly mixed. On the other hand, if I use a lighter gas, like maybe chlorine gas is lighter than bromine, those molecules are moving faster, assuming again we're at the same temperature. And so to get from here to partially mixed, it's going to take a lot less time to get there. And same thing to get to thoroughly mixed, it's going to take less time to get there. So how fast a gas diffuses depends on its molar mass, and that's the important takeaway here. Now, the term effusion is very similar, but in this case it refers to just a gas escaping from a tiny hole. So if I have a container filled with gas and I put a little pinhole in it and let the air or the gas, whatever it is, seep out through that pinhole, that's effusion. The reason we use that is because it's a lot easier to control and to quantify. So scientists can compare two gases in exactly the same kind of container with the exact same size pinhole in it and see how long it takes the container to empty out. And so you can directly measure effusion quite readily. Diffusion is a lot harder to measure. I mean, usually you go by just smelling the perfume or whatever. So diffusion is a lot harder to quantify and to measure. And so our gas law usually refers to effusion. Graham's law works for effusion perfectly. Graham's law works approximately for diffusion. So we can get rough estimates, but it's not going to be perfect. Okay? Now, again, notice that the type of particle is important in how fast it's going, because if it's a more massive molecule, it's going to diffuse and effuse slower. A lighter particle is going to go faster. And here they summarize what I just said there. Gases with lower molar mass diffuse and effuse faster. Higher molar mass diffuse and effuse slower. And that is Graham's law. This guy Graham was the first one to mathematically analyze that and realize that we've been just talking generally true, the more massive, the slower it goes. What he found, because of the way kinetic energy works, which you don't have to worry about that, it's an inverse square root relationship. So the heavier gas, the square root of its mass will relate to its diffusion velocity or effusion velocity. There's an equation for that, which we'll get to, I guess. Blah, blah, blah. Okay, well, we'll look at this and then we'll get to the equation. It's really straightforward, so it's not that bad. If you have a balloon filled with helium and then another balloon filled with air, which one is going to, if I put a little pinhole in each one, which one's going to empty out first? Or in other words, which gas effuses faster? Well, helium atoms have a molar mass of 4. You're looking at your periodic table, you'll find that. The air is mostly nitrogen, which is N2. Nitrogen is 14 times 2 of them is 28. So nitrogen molecules have a mass of 28 compared to helium having a mass of 4. Nitrogen is a lot heavier. And so the lighter particles, helium, are going to effuse faster. And so the helium balloon will empty out a lot quicker than the air-filled balloon. And you might notice that in the real world, where helium balloons empty out real quickly. The next morning, they're no longer really inflated. Okay? Now, again, how we usually use Graham's law is similar to what we did with Boyle and Charles and whatnot. We compare two to each other. Back with those laws, we compared V1 to V2, P1 to P2, and so on. Here we're going to compare gas 1 to gas 2. And we'll look at how they relate to the molar masses. Here's the equation I was telling you about. the rate of diffusion of gas A compared to the rate of diffusion of gas B, they show it as a ratio, rate A over rate B, is equal to, now notice it's a square root relationship, which I mentioned earlier, and it's inverse, which means the A and the B flip. The square root of the molar mass of gas B divided by molar mass of gas A. So what we'll usually do here is we'll solve for just this ratio on the left. We won't get individual rates, we'll just get rate A over B equals this. You'll plug in molar mass of gas B, molar mass of gas A, divide them, and square root. And the answer is the ratio. Now, let's go through the example. How much faster does helium diffuse than nitrogen? Again, we have to assume they're at the same temperature. So we look up the mass of helium. We find it's 4.0. They round off to only one decimal place here for some reason. The molar mass of nitrogen is 28 because it's diatomic. So I guess we'll call helium gas 1 and nitrogen gas 2, or gas A and gas B, I guess they are. So helium is gas A, nitrogen is gas B. And now we can plug into this equation. Rate of gas A, helium, over rate of gas B, nitrogen, is the square root of the molar mass of B, nitrogen, over molar mass of A, helium. Don't forget to flip your molar masses. If you're doing helium over nitrogen for the rate, the molar masses are flipped upside down, nitrogen over helium. So you plug in the 28 for nitrogen and the 4 for helium, divide them, and square root. And here they show that. Rate of helium over rate of nitrogen equals square root of nitrogen's mass over helium's mass. By the way, they use the incorrect unit here. They just use grams per molar mass. It really should be grams per mole. Doesn't matter. It cancels out anyway, but we should be accurate here. So take 28 divided by 4 and you get 7. Square root of 7 on your calculator, you get 2.7. That's our answer. Notice we don't solve for one gas or the other. We solve for the ratio. So the rate of helium over rate of nitrogen is 2.7. What that means is that helium diffuses 2.7 times faster than nitrogen. So a helium balloon will empty out 2.7 times faster than a nitrogen balloon will empty out. Or if we want to talk about diffusion, which again, it's approximate but still works, helium will diffuse across the room 2.7 times faster than nitrogen will diffuse across the room. So if I stand in the front of the room and I open up canisters of helium and nitrogen, which gas gets to you first? The helium does, 2.7 times faster. So if it takes 1 minute for helium to get to you, it's going to take 2.7 minutes for nitrogen to get to you. It's a slower diffusing gas. And that's all there is to Graham's law. It's really not that bad. You divide and you square root. The only ugly thing here is square rooting, but we have calculators for that. Okay, does the result make sense? Helium's less massive, therefore it should go faster, and we found it does go faster by 2.7 times. And finally, they leave you with a question: which of these gases will diffuse fastest? Well, look at their molar masses. Mercury's really heavy. Chlorine's pretty heavy. Sulfur dioxide, well, it's heavier than NO2 or N2O. So if you add up all their masses, you're going to find that N2O is the lightest of them all, and therefore is the fastest diffusing. And they agree with me, which they better. Okay? And that's it for the chapter. So I'll give you, again, a worksheet on Graham's law for tonight so you can practice with this. And then from there, we'll do a few review things and take a quiz on likely Thursday. Went over 10 minutes today, but it was a fun law, right? All right, see you tomorrow.